Thank you. So yes, my name is Matt Parker. Most people come across me because of my math communication work. However, I am also in the exciting new field of homodometrics. So I wish to talk to you about attempts to calculate pi with pi's. I should acknowledge there are other people working in similar areas. So we have calculations of C using the C. There is, of course, E with E's. We should collaborate with your kitchen. We have tau with tau's, and of course some groundbreaking work with Einstein's cosmological constant, lambda with llamas. However, my personal interest is pi with pi's, and of course I've gone about it with the fairly straightforward method, which is simply to get a lot of pi's and place them in a very large circle. I got a friend from a friend of mine, a friend phoned me up one day and said, "Oh, I have 400 pi's. Do you have any ideas?" And I was like, I live for these moments. And so, as you can see, with accuracy to the nearest third of a pi, we calculated the circumference was 264 2/3 pi's, the diameter was 84 1/3 pi, and so we were able to get pi to be approximately 3.14 solely using pi's. That video is on the number file math channel on YouTube if you wish to see it. Please hold your applause. If this has impressed you, you're going to lose your mind in a moment, because as much as I enjoy using circles, they are a little cliched when it comes to pi. I mean, it's the traditional use, I acknowledge that, which is why I did it. And actually I've brought, because pi for the circumference is still used practically. I found this on like an industrial equipment website. It's a measuring tape in units of pi centimeters. And so people buy these, tree surgeons use them because you measure around a branch and read off the diameter exactly to certain definitions of exactly in centimeters, right? And so I bought it off a tree surgeon website. So I believe there are some people who prefer a tau measuring tape. So a tree surgeon can measure the branch and know when they're only halfway through their job. Classic tau. However, I wanted to do something not involving circles so obviously, and so I realized that the equation for the time of the period of a pendulum is 2 times pi by the square root of the length of the pendulum divided by local g. Local gravity I took to be around about 9.8. That means if you make the length of your pendulum approximately 1/4 of the length of local gravity, that cancels out to give you I'm a big fan of cancelling out, by the way, gives you a 1/4. Of course, we can bring that down to a half. The 2 sees the half, and it's like, I'm all over that. Boom, that's gone. All right, and then, please see previous comments about cancelling, which means if you have a pendulum of length 1/4 of local gravity, it will take pi seconds to go backwards and forwards. So obviously the only natural thing to do is to suspend a pi from a piece of string. So once I had a pi, oh, by the way, I'm using the metric savory pi, not the imperial American apple pie. And so once I set that spinning, I filmed it doing 10 swings, so I could average them to get a value for pi. This is on my Stand-Up Maths YouTube channel. This is possibly the least exciting bit of footage I have ever committed to the internet. While it is swinging to give us our 10 complete swings, you might be concerned about accuracy. As you can see, I was. And so you do lose some energy because the way I've suspended the pi, it's able to rotate, so you will get some angular kinetic energy taking away your fantastic potential and normal kinetic. And if you do, oh, look at that. So 3.126 for swinging a pi backwards and forwards. If we wanted to improve on that, and I highly recommend you to have a go, if you want to get rid of losing your energy into the rotation of the pi once you work out its moment of inertia, and you look up its mass, and thankfully the fine people at the Pi Research Council believe in open access publishing. If you go onto their website, all of their data is available. I got the mass of the pi, and I worked out for the pi to take a significant amount of the energy away to ruin your result, it would be spinning at a rate of hertz where it's bordering on audible, so at least you will notice when that happens. A bigger concern is, of course, in physics, right? The formula I gave you, the equation for the period of a pendulum, is not even correct. right? Because when it swings and you go up through some angle theta, to get the original equation, they use the small angle approximation. And don't get me wrong, big fan. It's in my top 10 approximations. However, it means as soon as you move away from directly down, it's no longer giving you the actual period. I mean, well done, physicists. You've got an equation that works only if you don't move it at all, which most of us can achieve that. Are you going to move it and check? No, this one definitely works. So, although I spoke to an engineering friend of mine who works on clocks, and I said, what can I do to make this more accurate? And he goes, well, there's one trick you can do. If you somehow compensate with shapes at the top so the length changes as it swings, you can allow for the change in the period by altering the length of the pendulum. So just slap 2 pi's on there, and you're done. Right, so if you, in terms of further research areas, if you want to have a go at this, because I feel like I've exhausted pendulums, there are other physical equations that involve pi that we can use to try and estimate a value of pi. So the buckling force, that is for fixed at both ends. Any buckling fans in today? So if we knew the elastic modulus of a pi sufficiently well, we could compress it and see when it buckles and get a value of pi. Of course, the Heisenberg uncertainty principle features pi. We would need to know the pi's energy very accurately, but that is available on the website there. You will also note we need to know H. We need to know Planck's constant. But some colleagues of mine are doing amazing work measuring that with an actual Planck. And then we have the curvature of space-time. Thanks to the recent gravitational wave breakthrough, if we are able to get 2 pi's of approximately 30 solar masses each, have them coalesce and look at the signature on Earth and compare it to the previous results, we will be able to get an estimate of pi. Although, given that would require taking 60 equivalent solar systems and baking them into 2 pi's, the words further research funding is required has never been more true. So that is a very brief overview. Do come and see me if you have any additional comments. My gift for the gift exchange, I managed to get printed up a whole lot of pi measuring tapes. So please do have fun measuring some things, and as always, bear in mind, hominometrics, as we say in the business, it is what it sounds like. Thank you very much.